Bien, buenos días a todos los asistentes a este octavo seminario SINCA. Bienvenidos y en esta ocasión, en esta conferencia, tengo el gran gusto de presentar a la doctora Cristina Santos. Es una investigadora y amiga ya de hace varios años que ha destacado por su ímpetu y compromiso en las ciencias del comportamiento. Así es que es un honor para nosotros tenerla aquí en este evento como conferencista. Hago una pequeña y rápida reseña para no robarle tiempo a su conferencia. Ella es licenciada en Psicología por la Universidad Católica de Andrés Bello en Venezuela. Posteriormente, su maestría en Ciencias del Comportamiento en la Universidad de Guadalajara. Y su doctorado es en Psicología en la Universidad de VIII, Portugal, bajo la tutoría del doctor Armando Machado y del doctor Marco Vasconcelos. Su área de investigación es aprendizaje asociativo, timing y modelos computacionales de conducta. Y actualmente está desempeñándose como investigadora postdoctoral del Centro de Investigaciones en Comportamiento de la Universidad de Guadalajara. Y además, ya con un gran anuncio de que próximamente estará como investigadora postdoctoral en un proyecto de aprendizaje colectivo e inteligencia aumentada en colaboración entre la Arizona State University y la University of Georgia, ¿sí? Financiado por la National Science Foundation en Estados Unidos. Así es que esta es una gran oportunidad que tenemos nosotros para escuchar y tener contacto directo con Cristina. Pues sin más palabras para ya cederle el micrófono a la doctora Cristina, pues les agradezco mucho y recuerden que en el chat pueden ir comunicando sus preguntas, comentarios y al final de la ponencia se los comunicaré a la doctora. Bienvenida, Cristina.
Muchísimas gracias, Felipe, por la introducción, por la invitación. Para mí es un gusto estar acá. Creo que es la primera vez que presento en México. Entonces, es todo un placer estar aquí por casa presentando de nuevo. O por primera vez, mejor dicho. Bueno, les converso un poco. La presentación de hoy se titula... antes de comenzar, perdón. Mi presentación va a ser en inglés para abarcar un público un poco más amplio. Pero puedo responder preguntas al final, obviamente, en español. Entonces, siéntanse libres de... Okay, so my presentation today, it's titled, Is it time? What did just happen? Combining time and consequences to determine behavior. So I'm going to talk about a series of studies exploring the effect of the perceived temporal interval and reinforcement on choice. The backbone of any form of associative learning is the credit assignment, the process by which learning systems link the outcome of an event to its responsible factors. In the experimental analysis of behavior, credit assignment is usually inferred from the study of stimulus control. And traditionally, the main variable that we study is the control of behavior by reinforcement. And the study of the stimuli that are already present before the response occurs are usually relegated to a second place. That is why this study is focused on that second type of stimuli. We're going to assess the role of two very peculiar discriminative stimuli, the time elapsed from an event and the outcome of the previous response. Despite most living organisms are geared to properly associate biologically relevant stimuli to the preceding events, the assignment of credit is not that, it becomes a bit more challenging when there are multiple cues present at the same time. For instance, take the case of overshadowing, where the least salient cue will acquire less associative strength and produce a weaker conditioned response. Curiously, temporal conditioning proceeds independently, and it's not subject to overshadowing in any way, and that is very interesting. The first documented evidence of joint behavioral control of time in a discrete cue in a response-dependent preparation, this is an operant preparation, is attributed to Roberts. He trained rats and pigeons Here we go. In a peak procedure with two different FIs, each FI was signaled with a different cue, say one with a light and the other one with the tone. And then in the peak trials, these empty trials, he found that for each cue, respondent peaked near the moment, the time associated with the FI. It seems settled that when the time elapsed from a distinct event and a discrete cue signaled the availability of reinforcement, they share behavioral control. And that's what was thought until that moment. However, when the discrete cue is not a traditional tone or a light, but the cue is the outcome of the previous response, this is reinforcement or non-reinforcement, the credit assignment is no longer so straightforward. In this work, I'm going to try to integrate associative learning with timing, two processes that are intrinsically tangled, as I just mentioned, but they're often segregated. I decided to study how the time elapsed from a particular event and the outcome of previous responses interact in those situations where both cues can potentially gain control over behavior. I wanted to understand how credit is assigned, specifically in these ambiguous circumstances. That is important. And in the search of a suitable preparation to answer this question, we came across the Mcsession reversal task. It starts with a simple simultaneous discrimination where one stimulus is reinforced and the other one is not. And after several trials of this type, typically halfway throughout the session, contingencies are reversed and the originally reinforced stimulus is now extinguished and vice versa. For convenience, we're going to call the first reinforced stimulus S1 and the other one is going to be called the S2. Performance in this task is usually characterized as the proportion of responses to one of the stimulus along the session. Typically, we look at the proportion of S1 responses in every trial at a steady state. This is usually after 20 or 30 sessions. And one would expect that in such a simple task, performance proceeds somewhat like this. After some training, responding should cluster around S1 exclusively to S1, and after the first non-reinforced trial, responding should shift to S2, using the outcome of the previous trial as an indicator of the active cue. And that is, in fact, what we usually find in rats. Surprisingly, animals do not always behave this way. Often with pigeons, performance shows a smooth progression from S1 to responding to S2, but this transition involves incurring in some frequent errors around the moments of the reversal, both anticipatory and perseverative. The decline in responses to S1, like this right here, is the most curious feature of this type of performance because it suggests that animals are anticipating the reversal. Thus, both the outcome of the previous trial and the time elapsed from the beginning of the session seem to work as cues for the active cue, or to indicate that contingencies have changed. This phenomenon was very puzzling, and it made the mid-session reversal test the perfect test bed to answer the question of our study, which is, what determines choice when both cues are good predictors of the availability of reinforcement, one is a better predictor than the other, or when both are poor predictors of reinforcement? To illustrate how we're going to answer this question, let's go back to the structure of the task. To assess if behavior is under the control of time, of the time elapsed from the beginning of the session, to the moment of the reversal, we can either compare performance, or we're going to actually compare performance when the reversal is fixed halfway throughout the session in one point versus when it's variable. This is achieved by changing the reversal to a different and unpredictable trial on every session. And to assess the effect of outcomes on previous trials, we can change the payoff of each S+, reinforcing or not correct responses with a certain probability. To sum, this is what we're going to do. We will assess the effect of time on choice by manipulating the reversal trial, the effect of past outcomes by manipulating the reinforcement rate, and finally, I will compare our data to the predictions of simple computational models of behavior describing either temporal control, outcome control, or a combination of the two. In our first study, what we tried to do was to bias temporal perception. And here what we did was expose a group of pigeons to 4 different variations of the task. In all of them, the reversal was fixed halfway, but the probability of reinforcement of each S plus varied. All of our birds went through all the conditions, and we compared performance when the overall reinforcement rate was different, but the relative payoff was the same. So see that for each S plus it is the same, but the overall is different. And we also compared when the relative reinforcement rate was different, but the overall was the same. Here, the outcome of the previous trial could act as a cue, could gain and compete for behavioral control in different degrees. The effect of these manipulations, if any, should be evident in the psychophysical curve that relates the proportion of S1 responses to time into the session. And the first descriptive indicator of performance is the location parameter of the curve. This is where the curve crosses the indifference point. So it's this value right here. To the extent that the location moves away from the reversal, performance would be showing a bias. In this case, it is responses to S1 drop way before the reversal has occurred, indicating a preference for S2 even before it starts being reinforced. In this case, responses to S1 continue way past the reversal point, indicating that the subject continued responding in extinction. That would be a bias for S1. The second indicator of the effect of our manipulations is the scale parameter. It's the inverse of the slope of the curve at the indifference point. Shallower slopes like this one show a smooth transition due to a poor temporal discrimination. But then sharp slopes like this one indicate very good temporal accuracy, or perhaps, let's say, a high sensitivity to the reversal. So what do we do in the study? We first compared the conditions with equal reinforcement for both stimuli, these two, you see? And we found that consistent with a timing account, there was no difference in performance between the two conditions, both in terms of the location and the scale parameters. And this is consistent with many previous studies. Now, regarding the conditions with unequal reinforcement, we found let's start with this one. Let's start with the green curve. We found a leftward shift on the location parameter. So you can see that it's crossing here earlier. When it had a higher payoff for the S2, and it's similar to the other two conditions. So the location is the same, and if you notice, the scale or the slope of this curve is parallel to this one. So there was no change there, only a small bias, but no change in temporal perception in general. However, now when the S1 was richer than the S2, we found a very small shift in the location. This is about like a 43 actually. So a minimal bias, but a huge reduction on the scale parameter with a very sharp transitioning in responding. So how do we make sense of these results? We said, well, how can we answer or explain these results? Let's look back and see how similar results have been explained before. And let me see if this moves. One of the best fitting accounts of the very robust effect of reinforcement rates biasing time perception is the learning to time model of Machado and collaborators. They showed that the model accurately describes performance in a timing task, very similar to the mid-session reversal. It is on the free-operant psychophysical procedure. I'm not going to go into the details, but it's very similar to the mid-session reversal task. They explained not only their own data, but data from other studies. Their model fitted very well the other results. There we go. And this is why we ask, well, can the learning to time model also deal with at least the main properties of the Mcsession reversal task? So what we did is that we try to compare the model predictions with our findings, and let's see about that. I'm not going to go into extreme details again about the model, but I would say in general that the model represents a timing system with a series of interconnected units that serially activate to the onset of a signal. Let's see if this works. There we go. And as these behavioral states sequentially activate, the strength or the weight of these states to associate it to different instrumental responses will change according to their consequence. This is, if emitting this response produces a reinforcer, okay, the link between that response and the active or the behavioral state that was active at that moment will become stronger, increasing the probability of emitting that response in the future whenever that behavioral state is active. And the opposite mechanism works for non-reinforcement. And this is how they explain temporally regulated behavior. So we took this model and we simulated the Mcsession reversal task with our manipulations trying to bias temporal performance, temporal perception, and let's see what we found. Okay. All right, I forgot about this one. These are the details of the model, but then let's compare our results with the predictions. So the lines are the predictions of the model, the dots are the same data I already showed you. As you can see, it fits very well for the conditions with the same relative reinforcement rate. And it also reproduced very well the low-high condition. But here we see a big mismatch. And to this we concluded that our birds were either, in this case, they do not seem to be timing. So they were either violating the scalar property of time perception, or their performance was no longer time regulated. And for the sake of parsimony, we favored that second alternative. And that was our conclusion. We were in the presence of a condition in which animals were no longer being time regulated, or animals' behavior. So timing processes are involved to some extent. Behavioral control seemed to shift from one cue to another. So in some cases, they were following time, and in other cases, they were following the outcome of the previous response. And this might be the first demonstration of non-temporally regulated behavior in a color discrimination Mcsession reversal task in pigeons, and in fact, it was. So that study was very exciting. And we decided to follow up and decided to try to disrupt outcome control this time. So we wondered if it was possible to find similar behavioral control shifts from time to outcomes in rats' performance, given that they typically approach the task using a win, stay, lose shift strategy. So our first manipulation regarded the reliability of the outcomes, but always keeping them equal for both alternatives. So we did not have a difference in the probability of reinforcement. So we had either continuous or partial reinforcement. This is reinforcing 100% of correct responses. And this is reinforcing correct responses 50% of the time, or with a probability of 0.5. And simultaneously, we wanted to explore the effect of time under these conditions. So we also manipulated the moment of the reversal, if this moves, okay. So we had the reversal could be either fixed or variable. So this is how we ended up with these four experimental conditions: F for fixed, B for variable, 100 continuous reinforcement, 50 partial. This time, we characterize performance slightly different because we have conditions with a variable reversal, right? So we cannot analyze performance in terms of the absolute trial number like we did before, but we align performance according to the reversal trial and analyze responses relative to this point. So we subsect the curve and only looked at this area, aligning all the reversal trials like this. So for instance, a pattern of S1 responding of a subject controlled by time would look kind of like this, and a win-stay lose shift pattern, or a subject following that strategy, would look a little bit more like this. Notice the difference in the curves. Here we're blocking trials and only looking at the trials relative to the reversal, not the absolute trial number. So this is how a timing performance would look like from now on, and this with only one error or one S1 response after the reversal, if they're following a win-stay lose shift, right? The first non-reinforced trial is that. What did we find? Well, in the conditions under continuous reinforcement, performance seemed to follow clearly a win-stay lose shift strategy, regardless of the variability of the reversal. And under partial reinforcement, we found a similar pattern. So not too many anticipatory errors and a bunch more perseverative, which is expected due to the intermittent reinforcement. So it was not that clear that reinforcement had, the reversal had occurred. So it's normal that animals persevered a little bit longer. However, we went a little step further and we wanted to explore if there was any evidence of temporal control that we could not see here because we're averaging sessions with early and late reversals. So what we did is that we separated those reversals that occurred in the first half of the session and those that occurred in the second half of the session. We found that when reinforcement was continuous, there was no difference in performance and no indication of temporal control here. So the time of the reversal made no difference in choice. But well, under partial reinforcement, performance was different in the sessions with an early reversal versus those with a late reversal, showing that there was in fact a component in this condition, a temporal component, and that the lack of difference here was due to an artifact of averaging, but there was in fact a difference in some temporal control. This was also very encouraging. So to make sense of these results, we tried to simulate performance in this task with different models to see how they could reproduce the features of our data. I'm only going to show the best account, but in the original publication of this, you can see we tried more variations. So the model that we used and best explain our data is based on the idea that animals switch between timing and non-timing modes with a certain probability. For the timing mode, we simulated the simplest model of timing we could come up with. We didn't even use the learning to time model. We came up with something even simpler. We just assumed that the animal kind of keeps track of time from the beginning of the session and with a reasonable error, and that was their estimate. To do that, we simulated a system that draws a sample from a normal distribution with a mean equal to the elapsed interval at that trial, and a standard deviation in constant proportion to the interval. So we would build in there the scalar property. And if this sample was smaller than the average reversal, animal would respond S1, and if the sample drawn was higher than the average reversal, it would respond S2. So, and that was pretty much it. And now when the animal entered the non-timing mode, it would be a win, stay, lose, sometimes shift in this case, where we just created a flexible win, stay, lose, shift rule where there's a threshold or a tolerance parameter where the animal will wait a certain number of non-reinforced trials before switching to S2 instead of switching right away on the first non-reinforced trial, like on a traditional win, stay, lose, shift. So the details about this is that the threshold was inversely proportional to the momentary probability of reinforcement, and it was used to determine when to switch. And if the number of non-reinforced trials was lower than the threshold, the animal would keep repeating the previous response, so it would stay. Otherwise, the animal would shift. So it's a really simple model. And let's see what it did for our data. So on the left side is the rats data, and on the right side, you can see our simulations or the what our model drew. And if you notice, it is pretty similar, and it offered a really good fit. Finding a close similarity in all the patterns, and importantly, it was able to reproduce this difference in performance in the early versus late sessions only in the V50 condition without altering the others. So this was very exciting and promising. So what did we conclude was that performance seems to be a byproduct of the interval from the beginning of the session to the reversal, remembering the outcome of previous trials, and selectively shifting behavioral control from one cue to the other, according to the momentary probability of reinforcement. But still, this did not explain why or how behavioral control shifts. So, we kept going, and we came up with a third study in which we went back to our pigeons, and we wanted to dig a little bit deeper and try to find if there was any evidence of temporal control and test the generality of the results of the high-low condition. Because remember, in the first study, we concluded that there was no temporal control in the high-low. And then in our second study, we thought there was no temporal control, but by manipulating the moment of the reversal and separating or analyzing differently early versus late reversals, we were able to find that evidence of timing. We said, well, maybe we should check this same thing in our first study. So we basically repeated the experiments of our first study, but this time we made the reversal variable. Let me see. So we repeated this, but we made the reversal variable, and just like we did in the second study. So in every session, the reversal could be in any place around this gray area. And well, because behavioral, I'm gonna go into a little more detail of how we're gonna do this analysis because it gets messy. Because behavioral control by time and by outcomes engender distinctive patterns of behavior, like I just showed, making the reversal variable allowed us here to directly test the control of each cue over choice. Suppose that we have a subject that is completely guided by the outcomes. And after much training, we present a subject with a session with an early reversal, say this gray line, and a session with a late reversal. Notice that in both cases, performance will show, this is not in order, but let me see. All right. This is not in order, but you follow, I guess. So, notice that in both cases, performance shows here a step function. But then now suppose that a subject is, I'm going to go back. Yeah. Suppose that the subject is only guided by time, and it shows this type of pattern. Regardless of the location of the reversal, performance would always show that sigmoidal shape centered at the average moment of the all experience reversals. Now, under outcome control, now I can show you this in order. Performance around the reversal is similar, regardless of the location. Before the reversal is at 1, after the reversal 0. Before at 1, after 0. But on each individual trial, let's say on this one, performance would be different depending if the reversal had occurred or not. In this case, because the reversal already occurred, performance is at 0. But here on trial 40, if the reversal has not occurred, performance would be at 1. Now, under temporal control, no, doesn't want to move. Yeah. Performance around the reversal will be different. This is higher, would be different according to the location. But on each individual trial, here we go, if this moves, there we go. But on each individual trial, performance would be the same, regardless of the moment of the reversal. So even if the reversal occurred at 20 or at 60, say at trial 40, performance would be exactly the same. Curves overlap all the way. So the effects of the outcomes will be evident when comparing performance before and after the reversal, and the effect of time will be evident when we compare the sessions with an early versus a late reversal. Hope this made it a bit more clear in my messy presentation that made it more difficult. So to pinpoint the effect of the outcome of the previous response, we analyzed the data in a very novel way. And for each individual trial, we compared the proportion of S1 responses when the trial had taken place before the reversal and after the reversal. And in those trials where we have both measures, so this is performance before the reversal in those trials where it hadn't occurred, and here after the reversal, when the reversal had occurred before that. What we have is a difference between the two scores, and it reveals the isolated effect of the outcome of previous responses. These gaps show the abrupt change in choice after the reversal, a strong sensitivity to the change in contingencies. In all cases, as you can see, S1 decreased with trial number, except in this condition. Before the reversal occurred, animals always stayed responding on S1 to S1. In all cases, the reduction to S1 responses was about 60%. All these values is a drop in 60% of the previous level, which is very interesting because it's consistent and it indicates that the relative value of the outcomes was constant. So the question here was not why outcome control differs across conditions, but why pre-reversal performance differs across condition is the question to answer, and I'm going to get back to that. Now, that was the outcome control in this experiment. What about temporal control? We compared early versus late, and we aligned all the sessions according to the reversal, like we did on study 2, subset the surrounding trials. And you can see the staple of this experiment is the higher proportion of S1 choices across all trials and the early versus late. This is the white circles are always above the black, replicating previous results, which is consistent to temporal control of behavior, even in the high-low condition where we thought that there was no temporal control. Focusing here, you can see that although there's a very small difference in anticipatory errors, the fact that there was more perseveration errors in the sessions with an early reversal strongly suggests an effect of time. Lastly, we wondered if a model similar to the one we used in our second study could account for these results. And we really fell short capturing the features, the temporal features. So we had to change our model and we replaced the temporal component. That was the very simple timing model, remember? We replaced it with a learning to time model. And we switched a few details, but what we did was that we mainly allowed both systems. Oh, this went back. Sorry about that. Okay, it's not. Doesn't want to move. We allowed both systems to work simultaneously, feeding back each other. But what would only change was the probability of following the decision rule of each component. And this is what we found. So the dots would be our data and the lines, the predictions of our model. And as you can see in the conditions with equal relative reinforcement rate, it fits nicely. Of course, it could do better probably, but this was not bad at all. And it was very surprising that we were also able to reproduce these gaps right here in these two conditions, because we tried 2 other models and they were not able to even closely reproduce this. So what do we conclude here? Well, behavior was always under joint control of time and outcomes, even when we didn't see it in previous studies. The payoff, the payoff differential determines, apparently seems to determine the source of control. And the best description of the data was achieved by allowing the 2 components of the model to feedback each other. So animals may not necessarily switch into one mode or the other. It seems like they're both running simultaneously. And that's what we concluded from this study. Now, overall, animals can continuously and simultaneously learn from more than one contingency relation, and this is a clear evidence of that. This work is a very small step towards the combined timing and associative accounts of performance, and it's what we're working on. And the dynamics of the transition between behavioral control and between global and local cues remains unexplained, but we do have a few insights on how this could come together, and we'll probably see it in future work. Thank you. Lastly, I don't want to take, we're just right about on time. I got to thank the universities where this work took place in one way or another. My advisors, tutors, and basically spiritual guides here, Armando Machado, Marco Vasconcelos, and Federico Sanabria, who are a huge part of this work. My 2 sets of lab mates and the funding agencies that paid for the drinks. And here are lastly, the references to the 3 studies if you would like to look into the details. And that is pretty much from me. I don't know if anyone has any questions.
Cristina, muchas gracias por tu presentación. Y gracias, sí, efectivamente, tenemos aquí algunas preguntas. Okay. Las voy a plantear como llegaron, que es en español. Espero no sea problema. Al contrario.
Respondo en español, creo. Sí.
Bien. Hay una pregunta en donde se te pide una posible aplicación de estos estudios que has presentado en conducta humana. Si los hay, ¿cómo se pudiera aplicar?
Esto me lo han preguntado varias veces y quizás no sea tan evidente todavía, pero creo que hay casos reales en el día a día en los que nuestra conducta realmente está gobernada por ambas fuentes de control conductual. Cuando estamos generalmente esperando en el semáforo, en un semáforo que conocemos muy bien, que pasamos todos los días para ir de la casa al trabajo, algunas veces, no sé si les ha pasado, a mí me pasa, se habrán dado cuenta que sabemos ya más o menos la duración del semáforo y a veces empezamos a arrancar el coche antes de que el tiempo del semáforo o la luz del semáforo cambie. Entonces, esos son algunos ejemplos en las de la conducta de la vida real, en la que vemos que los humanos también procesamos estímulos temporales o la cualidad temporal de los estímulos al mismo tiempo que otros eventos, ¿no? Ahora, una aplicación del día a día en la que yo creo que podamos rápidamente mejorar el mundo y curar el cáncer. Creo que no tengo una respuesta para eso directamente, pero estoy segura de que esto nos ayuda a entender cómo funcionan los sistemas de aprendizaje y podremos construir quizás una teoría un poco más integrativa que luego sí nos ayudará a crear aplicaciones, modificaciones conductuales, etcétera, bastante más prácticas, ¿no?
Bien, y literatura...
No sé ni siquiera si eso responde, pero...
Yo creo que sí, más bien, y literatura vinculada a estudios con humanos.
Solamente hay un estudio con humanos y realmente no creo que sea nada válido, no creo que tenga validez externa alguna. Es un estudio muy simple en el que ponen a los humanos a hacer una tarea exactamente igual a la de las palomas y al cabo les presentan 2 cartas de jugar y siempre la correcta es una en particular. Imagínense un as negro y un as rojo y los primeros 12 ensayos el as rojo es correcto y en los segundos 2 ensayos el as negro es el correcto, el otro. Claramente los humanos somos bastante buenos en contar. Entonces la ejecución que se observa ahí es una típica estrategia de win, stay, lose, shift o de conteo, da igual si no están prestando atención. Y vemos una ejecución igual a la de las ratas teóricamente, pero es una tarea que creo que no tiene validez externa alguna. Sí hemos estado trabajando en diseñar una tarea para humanos donde se enmascare un poco la reversión de la tarea, etcétera, etcétera, pero no hemos todavía concretado el experimento como tal, ¿no? Pero sí está entre los procesos. No hay ninguna evidencia de esto en humanos.
Muy bien, gracias. Otra pregunta. Cuando menciona que el tiempo puede ser estímulo discriminativo, ¿significa que se asume el tiempo como un tipo de estímulo?
Es correcto. Se asumiría en este caso, estaríamos asumiendo el tiempo como no sé si sería un tipo de estímulo o una cualidad, como una dimensión del estímulo. Porque a veces tenemos un estímulo, por decirte, en la caja experimental, que es la tecla con una cruz, y decimos, bueno, o el color de la tecla, y podemos cambiar el color, la intensidad, el contraste, etcétera, etcétera. En este caso, otra dimensión del mismo estímulo es su duración. y funciona como estímulo discriminativo, al igual que la intensidad, el contraste, o por lo menos en este caso es lo que parece estar ocurriendo. Yo también soy un poco escéptica, o era un poco escéptica a pensar que era un estímulo como tal, pero en este caso entenderlo así nos ayuda a darle sentido a lo que estamos observando en los datos, ¿no?
Ok, muy bien. Quizá alguna pregunta más de la audiencia. Hay tiempo quizá solo para una antes de irnos al descanso.
Como 3 minutos, como 1 minuto. Pues sí, no sé si, no entré en grandes detalles de los modelos porque hay muchos detalles en el que lo quiera leer lo lea, además de que se vuelve un poco tedioso y pesado. Pero esa ha sido la manera en la que hemos logrado explicar estos resultados que no veíamos, no esperábamos por ninguna parte. En realidad pensábamos que era una tareita así de timing, como otras, y no esperábamos encontrar nada interesante, debo confesar, en el primer experimento. Solo queríamos replicar resultados. El problema fue que no los replicamos.
Sí.
Y luego, sí, y este fenómeno ha sido replicado por otros autores, no solamente yo fui la primera en publicarlo allí, pero luego Sental lo replicó también, otros laboratorios han intentado y pues parece bastante robusto.
Sí, porque de alguna manera, dado el subtítulo que tiene tu presentación, la determinación de la conducta, pues está como siendo multideterminada y aquí los aspectos de la consecuencia, ¿sí? Como el evento central añadido a la temporalidad, ¿no? Entre
¿Sí?
otros posibles factores que determinan rasgos de la conducta, ¿no? Entonces yo creo que justo es una manera en la que se puede ir seleccionando esa multideterminación que habría, ¿no? En la conducta en lo general, quiero decir, sobre todo en los estudios que mencionas de la etológicos, ¿no?
Sí, y es como un ejemplo más de que parece el tiempo a veces funcionar como estímulo o una dimensión de los estímulos, así como tal vez la conducta no está controlada necesariamente por el brillo de la tecla, sino solo por su color. No quiere decir que los animales no procesen el brillo, no lo conozcan, no tengan memoria de él, no esté asociado al contenido del aprendizaje. En este caso parece ser igual, pensábamos que las ratas no procesaban el tiempo y conseguimos que había evidencia de eso.
Hay una pregunta que si esto puede hacerse un ejemplo con redes sociales, si lo hay.
Con redes sociales.
Ajá.
A ver, ¿pueden elaborar un poquito más a esto?
¿Quién elaboró la pregunta? Si me lo
¿Qué se te
puede.
ocurre, Felipe, alrededor de esto?
Un ejemplo en redes sociales, no sé si.
Redes sociales.
Redes sociales, sí, redes sociales.
Estaba pensando en grupos, en otra cosa. Un ejemplo de esto en las redes sociales, donde estemos combinando el tiempo, la consecuencia, pues tal vez donde las frecuencias de posteo de fotos, imágenes, etcétera, etcétera, puede estar determinado por el número de likes recibidos, cuánto tiempo hace desde que recibí el último like, por ejemplo. Es posible que podamos aplicar esta clase de modelos a la frecuencia o la actividad, ¿no? En redes sociales. No sé si es eso a lo que se referían, pero a mí sí me parece totalmente claro que el tiempo transcurrido desde un evento y las consecuencias de las cosas que hacemos en redes sociales determinarán nuestra actividad. Y pudiéramos intentar pensar esto en experimentos con humanos totalmente.
Bien, un par de preguntas más que aparecen por aquí. Bueno, algunas felicitaciones has recibido.
Gracias.
Muy interesante el trabajo. Dice, me parece que las ratas son un caso diferente cuando se habla de estimar el tiempo. ¿Crees que sea así? ¿Que es algo de la especie? ¿O solo aún no se identifican los parámetros con los cuales pueden ajustarse?
Esa es una excelente pregunta. Me la hacen bien a menudo y no la agrego acá. Realmente prefiero decir esto en palomas y esto en ratas porque lo hace más llamativo. Y es como originalmente teníamos pensada esta tarea. Pero otras investigaciones que hemos llevado luego, que todavía no están publicadas, pero que tengo ahí bajo la manga, demuestran que no es algo característico de la especie. Las palomas, esto sí ha sido publicado anteriormente, también muestran bajo algunas circunstancias ejecución tipo win-stay-lose shift, sobre todo cuando la discriminación es espacial. Y esa es la principal diferencia acá. Cuando la discriminación es de color, las palomas suelen mostrar estas respuestas más, o esta ejecución más de timing. Cuando es espacial, es más fácil recordar la consecuencia de la anterior. Lo mismo en ratas. Y todos los trabajos en ratas se han hecho con discriminaciones espaciales, porque ha sido muy difícil entrenarlas en discriminación de color. Yo no lo había logrado, otros laboratorios tampoco lo habían logrado. Pero recientemente acabo de lograr eso en colaboración con un estudiante que se ha encargado de apoyar en eso, y hemos encontrado ejecución del estilo timing en ratas en discriminación no espacial. No voy a decir de qué tipo todavía. Entonces no es una característica específica de la especie el utilizar la temporalidad de los eventos o las características o las consecuencias. Lo que es específico de la especie es el sesgo a fácilmente o más fácilmente utilizar claves espaciales o no espaciales, en realidad.
Bien, bien, muy bien. Y una última pregunta para ir a descanso. ¿El conteo necesariamente oscurece la estimación temporal? Creo que está vinculado con lo que mencionabas del conteo con humanos, pues, que si necesariamente lo oscurece.
Depende, creo, aquí un poco de la perspectiva teórica que tengamos, más que en la vida real, no estoy segura. Porque todos los modelos que explican timing explican counting o conteo. Entonces, el sistema de fondo, bueno, no todos los modelos, eso no es cierto, eso es una exageración, creo. Pero muchos modelos de timing son también modelos de conteo. Entonces, sería exactamente el mismo proceso. Desde otras perspectivas teóricas, pues sí, contar pudiera estar opacando el timing, pero podemos contar segundos y luego estamos mostrando una ejecución temporal, o podemos contar ensayos, contar eventos, o contar el número de respuestas no reforzadas, y entonces allí estaríamos mostrando una ejecución tipo win-stay-lose shift. Si se fijan en el segundo modelo que presenté, el de las ratas contaban también. Estábamos incorporando allí ese efecto en el que contaban el número de ensayos no reforzados para luego decidir si cambiar o no. La verdad es que yo creo que contar y llevar el paso del tiempo son procesos que están totalmente ligados, y es por eso que es tan difícil saber a veces qué está haciendo el animal. ¿Está contando o está estimando el tiempo, no? Se ve casi igual.
Ok, bien, pues gracias, Cristina, por tus respuestas, atendiendo las preguntas de la audiencia.
Muchísimas gracias, Felipe, a ti y a todos los organizadores y participantes.
Bien, Cristina, pues sí, te agradecemos muchísimo que hayas aceptado y nos hayas dado esta conferencia. Bueno, y le recordamos a los asistentes que ahorita es un momento de descanso. A las 11 se retoman las actividades. Pueden visitar el programa, ver las comunicaciones orales asíncronas. Inician las síncronas también a las 11, con también un simposio del doctor Raúl Ávila y otro simposio también a las 11 del doctor Juan José Irigoyen. Pues están invitados y pues nada más que agradecer su participación. Muchas gracias.